As introduced, my name is Jurģis Zemits, and I will be presenting you my paper results of the paper Analysis of Wind Speed Influence on Heat Recovery Efficiency of Local Decentralized Alternating Ventilation Units. After this small paper, you should be able to come up with these results of these first two objectives. Small acknowledgement at the beginning. This work has been done in support with my postdoctoral research sponsored by European government. At the beginning, small introduction. As you know, for all new and renovated buildings, there should be need for some kind of ventilation system to keep the indoor air quality good, environment healthy for the persons living in it, and so on and so forth. There are many types of ventilation systems available in the market. For example, large, full mechanical ventilation systems, maybe just some exhaust in bathrooms or kitchens. But sometimes you need to have this possibility to recover the heat from the exhaust or air to the supply air to keep the energy consumption as low as possible, as the energy lost by ventilation actually can be more than half of all the energy loss for the buildings, especially in northern climate. There are some different possibilities to use different ventilation systems, but in the latest time there have been more and more cases when people choose to place local decentralized ventilation systems because they are small, easy to install. You can place them both in new buildings, also in renovations, and according to the manufacturer data sheets, they guarantee a very high heat recovery efficiency, up to 90%. But there is little problem because there isn't one specific way how to determine this efficiency, and actually the manufacturers may be manipulating with this data a little bit. They usually state this efficiency just at the 0 Pascal pressure difference between indoors and outdoors, but in the real case situations, there is always some kind of pressure difference, either due to stack effect or due to wind, or due to some local regulations that actually requires that there should be some negative or positive pressure in the buildings. So our task was to determine how this pressure difference actually influences this actual heat recovery efficiency. If you don't know what are these local decentralized ventilation systems, I can shortly tell you they are small ventilation units that you place inside a wall. There is a section of it, and it consists just of some small fan. There is a ceramic heat exchanger, some filter, and inlet hood and outlet hood. Usually they are set up in pairs, so when one works in exhaust phase, the other works in supply phase. They are placed in the same room. So they switch this phases each 70 seconds, so the heat recovery gets, the heat heats up this ceramic heat exchanger during the exhaust phase, and then during the supply phase, it actually heats up this incoming air. During our study, we tested these units in a climatic chamber of our university. On the top left corner, you can see the plan view of this experimental setup, and on the right view, you can see the section. The inside of this climatic chamber represents the outside air conditions. We changed the temperature with the help of the cooling coil, and also changed the pressure inside this climatic chamber with help of external ventilator. We could set up this necessary pressure difference, and the ventilator automatically adjusts its rotation speed to maintain this setup pressure difference between the inside and outside. The outside parameters of this climatic chamber wasn't specifically controlled, but it represented a normal indoor air parameters, something like 20 degrees, and the temperature didn't change during the experiment. Afterwards, we used the method described in European standards, how to calculate this ventilation heat recovery efficiency. In general, we took measurements for each of the second for this running time of 70 seconds, and afterwards calculated the average heat recovery efficiency. We did this for several combinations of simulated outside air temperature and pressure differences. So the pressure difference was in range from 0 to 50 pascals, or in empirical units from 0 to 0.20 inches of water column, and at 3 different simulated outside air temperatures, +7, 0, and -5 degrees centigrade, or these Fahrenheit. Each setup was run at least for 7 minutes, therefore ensuring at least 3 full cycles. And for a couple of these measurements, we let this device run over the night, so everything would be stable after some time. What we came up with the results, actually we tested 2 different sized units. One was smaller, with size 100 millimeters, and the second one was a little bit larger, 160 millimeter size, to check whether this actually also influences their performance. And the results are like this. What you need to pay attention is this green line, which represents the temperature efficiency, or this recovered heat efficiency. As you can see, it drops from somewhere around 85% down to 60% if there are no pressure difference in these premises, which simulates inside and outside air. For the smaller device, and something similar for the larger device, it's also from 85 down to 60%. What happens if we increase the pressure difference? Actually, the heat recovery efficiency drops quite noticeably with small increases. Already at 5 Pascal pressure difference, you can see that the heat recovery efficiency reaches only about 80% and drops down to 50%, and so on and so forth. For example, at 10 Pascals, even more. At 20 and 50, even more. Already at like 20 Pascals, you can see that the recovered efficiency is only something like 30% for the smaller device. For the larger device, the results were a little bit better. It can be seen in this graph, where you can see on the x-axis this pressure difference, and on the y-axis this temperature efficiency. For the smaller device, it drops faster, while for the larger device, it can maintain this efficiency a little bit longer, also up to something like 20 to 30 Pascals. But in general, the results state that if we look at this measured heat recovery efficiency, the datasheets only represent the first couple of seconds when this device works. Then actually this efficiency is the stated 85, 90%. But already at the middle of this cycle, something like 30 seconds, the actual efficiency is already dropping down to 70, 60%. And what are the consequences? The consequences can be that actually people will turn off this device because the incoming air will be colder than they expect. They do not want this cold draft, because actually sitting by this device while it was operating in this during these measurements, actually I also got cold just for sitting near it. Also, some heating devices could be undersized. If you take this, that all the time this efficiency will be this 90%, and also this estimated heat consumption of the building during the whole year will also can differ from actual situation, because maybe the person who calculates this energy consumption of the building will not take into account that actually there will be smaller, this heat recovery efficiency will be smaller than actually stated in these data sheets. Therefore, you need to pay attention to this, and together with my colleagues from Estonia, they are also had they had a lot of renovations going on, and during the first phase of renovations, a lot of such type devices were installed, but after exploiting them a couple of years, actually they started to turn away from them and not to use it in the future projects. So from our northern country experience, we can say that this may not be the best solution for ventilating your buildings because of all these previously mentioned states. Some references and time for some questions. Yes, I rushed it through, but nevertheless.
Gary Simonson, University of Saskatchewan in Canada.
Hello.
So I guess first, a couple questions. One, how is the pressure difference maintained in those buildings? Because I would assume the ventilation system is creating that pressure difference.
In the buildings, no, actually we simulated that there is how this device works at different pressure differences, because there will be always some kind of pressure difference between inside and outside the buildings. We do not control it in real buildings. We do not control it.
Right. No, that's my question. In the real buildings, what sort of pressure differences are measured when using these devices? Because that's the device is the one that's going to create the pressure difference, right?
These devices will actually won't be the major source of these pressure differences. The major source will be stack effect and wind pressure on the side of the building.
Okay, so they're really low pressure devices then.
What is it?
They're really low.
They are
pressure.
low pressure devices. Yeah.
The other thing is, what about certification? So the manufacturer can measure according, they claim, to the European standard. Mm-hmm. Is there a certification body like we have here in North America, AHRI?
I think they are certified according to this EU standard. But this EU standard doesn't state that you need to measure this efficiency at different pressure differences. They just install two devices in something similar like we did in this climatic chamber, but there are no pressure differences from like outside to inside.
Okay. And maybe just from there's, I noticed you have reference to Targo Kalamis.
Yeah.
Has he done field measurements then of pressure differences that they've seen?
Just recently, actually, yeah, he published a paper some couple of months ago where he stated they actually did something quite similar. They measured this pressure difference between inside and outside, and also tested such type of devices. They also came with quite just like our results, that these devices work somewhere in 60% efficiency only.
Okay, good. Thank you.
Hyojin Kim from NJIT. My question is, I mean, you said the pressure the current EU, the certification, it's just for 1 point pressure difference, right?
Yeah.
Then what is that pressure difference in your research? What's the number for that?
0 Pascal.
Just 0 Pascal pressure difference?
Yeah.
And measuring the efficiency?
Yeah.
Okay. Okay, thank you.
Okay, no more questions?